Hello viewers, in today's class we are going to discuss yet another important and very conceptual problem from Lagrange's mean value theorem. So here in this session we are going to prove this important inequality using Lagrange mean value theorem, right? So here we have to show that e raised to 1 over 1 plus n is less than 1 plus 1 over n, and that is less than e raised to 1 over n for all values of n belonging to the set of natural numbers. So here we have to show that the n plus 1th root of e is less than 1 plus 1 over n, that is less than the nth root of e, where e is our exponential number. So we can also rewrite this inequality as the n plus 1th root of e is less than 1 plus 1 over n, that is less than the nth root of e, right? So using the Lagrange mean value theorem will show that this inequality holds for all values of n belonging to the set of natural numbers. So here the capital N denotes the set of natural numbers. So let us first discuss the statement of Lagrange mean value theorem. So suppose we have a function y is equal to f of x, which is defined in some interval a comma b, right? And if this function y is equal to f of x is continuous in the closed interval a comma b, and this function is differentiable in the open interval a comma b, then Lagrange mean value theorem says that there must exist some point c lying between a and b, such that the derivative of f of x at this point c is equal to f of b minus f of a divided by b minus a. So now let us apply Lagrange's mean value theorem to this function f of x is equal to a log of x in the interval n comma n plus 1, right? So here we are taking the function as f of x is equal to log of x. This is natural log of x, and here it is understood that the base of log is e, right? And we'll take the interval as n comma n plus 1, where n belongs to the set of natural numbers, right? So the value of a is n and the value of b is n plus 1, right? So now this function that is log of x is continuous function in the interval that is n comma n plus 1, right? Because from continuity and limits we know that the log function is a continuous function in this interval that is n comma n plus 1, where n belongs to the set of natural numbers, and moreover all these n are positive. Now let us differentiate this function log of x. So f prime of x is equal to the derivative of log of x, which is equal to 1 over x, and we can see that this function 1 over x is defined for all values of n belonging to the interval that is n comma n plus 1, right? And since n the least value of n is 1, so x can never be equal to 0. So this function log of x is differentiable or derivable in the open interval n comma n plus 1, right? So the first two conditions of Lagrange mean value theorem are satisfied by this function in this interval. So now the mean value theorem says that there must exist some point C lying between n and n plus 1 such that f prime of C is equal to f of b minus f of a divided by b minus a. So b is n plus 1, and then we have a as n, and then we can write here n plus 1 minus n. So now f prime of C can be written as 1 over C by replacing this x by C, right? So here we have 1 over C, and f of n plus 1 can be written as log of n plus 1 by taking x is equal to n plus 1, and f of n can be obtained by taking x is equal to n. So we have log of n, and in the denominator this n and this n get cancelled, and we are left with only 1, right? So we have log of n plus 1 minus log of n, which can be written as log of n plus 1 over n by the property of logarithms. So now we have 1 over C is equal to a log of n plus 1 over n, which can be written as 1 plus 1 over n, right? So now we have this expression. So now let us take this inequality, that is C. It lies between n and n plus 1, and here it is important to note that n, C and n plus 1 are positive quantities, right? So let us take the reciprocal of all these three numbers. So we'll have 1 over n, here we have 1 over C, and here we have 1 over n plus 1, and the direction of the inequality get reversed. So now we have this inequality, right? So this can also be written as 1 over n plus 1. Here we have 1 over C, and here we have 1 over n, right? Now 1 over C can be replaced by this expression. So we have 1 over n plus 1, and here we have log of 1 plus 1 over n, and here we have 1 over n. So viewers, here we have obtained an important inequality, that is for all natural numbers we have 1 over n plus 1 is less than log of 1 plus 1 over n, that is less than 1 over n, right? So now to move further, let us raise these three quantities to the power of e, right? So we can now write e raised to 1 over n plus 1, and this is less than e raised to log of 1 plus 1 over n, that is less than e raised to 1 over n, right? So here the direction of the inequality remains the same, because we know that the function e raised to x is increasing function for all values of real numbers, right? So e raised to x, that is the exponential function, is an increasing function for all values of real numbers. So what we have done here, we have raised these three numbers to the power of e, right? So now we can use an important result from calculus, that is e raised to log of say k is equal to k, right? And here we are dealing with the natural log. So e raised to log of k is equal to k. Here the base is e, right? So applying this result to this expression, we have e raised to 1 over n plus 1 is less than that is 1 plus 1 over n, because our k is 1 plus 1 over n, right? And this is further less than e raised to 1 over n. So this is our required inequality, right? So viewers, this is how, by making use of Lagrange's mean value theorem, we can prove these kind of inequalities. So now see here, our n is a natural number, right? So if we take n is equal to 1, let us see what we get from this inequality. So as a special case, if we take n is equal to 1, we'll have 1 over 1 plus 1, and then this is less than 1 plus 1 over 1. This is e raised to 1 over 1, right? So this is e raised to 1 over 2, and this is 1 plus 1 2, and this is e raised to 1, right? So e raised to 1 over 2 can be written as square root of e, and this is 2 and this is e, right? So by taking n is equal to 1, we can establish that the square root of e is less than 2, and 2 is further less than e. And here we have also arrived at an important result, that the exponential number is greater than 2, right? So although we know that the exponential number, it lies between 2 and 3, so from this inequality we can establish that the exponential number is greater than 2. So now viewers, we have also proved this important inequality in this video, right? So here if we take n is equal to 1, let us see what we get. So if we take n is equal to 1, here we have 1 over 1 plus 1. This is log of 1 plus 1 over 1, and this is 1 over 1, right? So this is 1 over 2, and this is the log of 2, and this is 1, right? So a log of 2 can also be written as ln2. So ln2 is greater than 0.5 but less than 1, right? So this is how we can prove, or we can arrive at important inequalities by taking special values of n, either in this inequality or in this inequality.